Hey, AP Chemsters, this is Mrs. Vanderlei bringing you a new blank wall. This is chapter 6.7. This is constant pressure calorimetry, measuring delta H of a reaction. And this topic is going to be very, very important for our future lab. This is really what we're doing. Constant pressure calorimetry are usually measured in coffee cup calorimeters. You've already kind of seen those in a prior lab, those styrofoam cups there. If you remember a constant volume, that's when you have a bomb calorimeter, and what the heck, most schools don't have bomb calorimeters, okay? So we're not going to use the constant volume, we're going to use the constant pressure, because I think most folks can afford the styrofoam cups, okay? So let's see what this says. For most chemical reactions, delta H of the reaction can be measured using the coffee cup. Heat lost by the reaction is negative heat gained by the solution, usually water. Why? I think you know that. What are you going to say? Let's hear it. Oh yeah, the specific heat is 4.18. It's really pretty high, isn't it? So we'll use water for the solution. So why do we have to go through this anyway? Can you measure the delta H of a reaction directly? And the answer is no. You can only measure it indirectly by seeing what the heat of the solution, typically it's gained, not always, and then you can reverse the sign and see what the delta H, or excuse me, the Q of the reaction is. So like I wrote, no. Constant volume, use a bomb calorimeter. We aren't going to use that, can't afford that. And constant pressure, use a coffee cup. Yeah, we can do that. So let's check out this magnesium question so we see how we really work this out. Folks, it's that same equation, MC delta T. You're going to get really good at MC delta T, trust me, okay? So here's our experiment number 34. Let's see what's going on here. Oops, actually I want to scroll up a little bit. There we go. Determine the enthalpy change for this reaction. 0.158 grams of magnesium metal combined with enough hydrochloric acid to make 100 mils of solution in the coffee cup. The HCl is sufficiently concentrated so that the magnesium will completely react. Therefore, the HCl is in excess. The magnesium is limiting, right? The temperature of the solution rises. So the temperature is gaining energy from where? From the reaction. So find the delta H reaction as written, and typically delta H, when we do problems like this, the unit will be, are you ready? Maybe jot this down, kilojoules per mole. So be really, really careful of the units again. So I'm telling you, that's the units we want. So we know we need the Q of the reaction is a negative Q of the solution. So what equation am I working with? I'm working with this one, correct? So we now need the mass of the solution. What is the mass going to be? Hang on a second, there we go. The mass is going to be, well, I have 100 mils. I have a density of 1 gram per 1 mil. So if I have 100 mils, I have 100 grams. So that's my M of my solution, is that 100 grams. What is my specific heat? They told it to me for the solution. There it is. And what is my delta T? It's right here. Okay. So go ahead, pause this if you need to, and see what you get for your Q value here. Oops. All right, hopefully you're back now, and this is what I got. Now, what did I tell you? We need to find the delta H of the reaction in the kilojoules per mole. So it's really important that we keep that in mind. First of all, what unit is my Q? And my Q is in joules. So I'm going to have to switch that into kilojoules. But what do I do about mole? Mole of what? Well, it's going to be moles of magnesium, and I'm giving grams of magnesium. So did I hear that? Periodic table. Hey, that's right. So you need your periodic table to figure out the moles of your magnesium. So go ahead and set that up right now. How many moles did you end up with? All right, this is what I did. I put this here, found 24.31 grams are in 1 mole. And so when I do all this, I get, I'll stick it over here, 0.00650 moles of magnesium. So now I can put this together. I can say the delta H, the reaction. What did I do here? I divided the joules by 1,000. Remember, your smaller unit has to have the bigger number. Your bigger unit has to have the smaller number. That's why I divided by 1,000. And now I'm going to divide it by the number of moles. And when I get all done with that, I get this value right here. Okay, so hopefully that makes sense, because I want to work on the next problem with you and see how you do on this. Okay, so if I scroll down, I have the addition of hydrochloric acid to silver nitrate to precipitate silver chloride. So what happens? I have solutions. Remember up here, I had grams of magnesium, okay, in hydrochloric acid. And down here I have solutions. All right, I'm gonna have to work on this a little bit different. So anyway, I have 50 mils of 0.1 molar silver nitrate combined with 50 mils of 0.1 molar HCl in a coffee cup. The temperature changes from 23.4 to 24.21. What does that mean? The temperature went up. So the solution is absorbing the energy from the reaction. So the solution is gaining energy. That's your endothermic. So your reaction must be exothermic. That's right. So calculate the delta H of the reaction for the as written. Keep in mind, what unit do I want it to be in? It'll be in kilojoules per mole. Well, per mole of what? Well, let's look back up here again. Okay, here's my equation. Very important. What are my coefficients of both silver nitrate and hydrochloric acid? It's 1. So really, you can choose either one and you're getting the same thing. Remember in the prior section, section 6.7, we talked about the stoichiometry and it was very much tied in with those coefficients. So you have to, again, be very careful on the, which reactant maybe you're going to use, because you want to get the one with a coefficient of 1. That will be the easiest. Well, in this case, they're both 1, so it really won't make any difference when we get to that. So what's our equation that we're going to use? I need to grab, here it is. There it is. So Q, the reaction, is negative Q of the solution. So what do we have here? We have, again, negative MC delta T. So what's the mass here? This is combined. So visualize, if you're putting 50 mils of silver nitrate with 50 mils of hydrochloric acid. So combine those volumes. Okay, jot that down. You need to combine those volumes. So what's your total volume of your solution? It's 100 mils. That's right. So if you have 100 mils, here is your density. How many grams do you have? You have 100 grams. Okay, and they gave you the C value, and they gave you your delta T over here. So let's see, here we go. And so do the math, what do you get? Okay, this is what I got. Hopefully that's what you got too. So what are we looking for? We're looking for kilojoules per mole. Well, folks, we need to find kilojoules. Well, that's not too hard to find. Divide this by 1,000. All right, so that works out pretty nice. But we have a little problem though. We need per mole. Per mole of what? Well, pick one. Remember I just said their coefficients are the same. They're both 1. I don't care. Pick one of them. And so how do you find moles if you're given volume and if you're given molarity? Well, what do? So how do we find moles given solutions? Oops, do you remember this formula here? Molarity times volume. Or you can sing our favorite song about the moles being on top of the mountain. Remember that? The moles on top. You got it. All right, so anyway, what is the molarity of our, let's use silver nitrate. What's the molarity of silver nitrate? 0.1. How many liters of silver nitrate do we have? Oh, we have milliliters. You have to divide to get your liters, don't you? All right, so here is my value. I got, come here. Here we go. And so then how many moles of silver chloride, or excuse me, silver nitrate do we have? Or HCl. I guess I wrote HCl. Does it make a difference? It really doesn't. And so now what? I can go ahead and put that number down here. I got my moles. There it is. And I could also put silver nitrate instead. They both have a coefficient of 1. And when you divide that out, I hope you get this. Okay. Any questions? Write them down. You can ask me tomorrow. So I think we have one more problem on the next page. So let's see what that looks like. Okay, I'm sorry, I made a mistake. I thought I was on another page. Anyway, we have a few more problems than just those two. Problem number 36 is kind of an interesting one. They say in the same reaction with the exact same amount of stuff, we have a bomb calorimeter and we have a coffee cup. In one measurement, we have Q is negative 12.5 kilojoules. The other one, we have negative 11.8. Which one was obtained in the bomb calorimeter? Now, they had to give you a little bit more information. Assume the reaction has a positive P delta V in the coffee cup calorimeter. So if this is a positive value, then this is your coffee cup calorimeter. All right, why is that? Because this is less negative than that one. All right, so I think it would have been a lot harder if they didn't tell you anything about that. I went back and looked at our true definition of delta H, and so from there I could then figure out which one was which. Okay, that was an interesting question. Not very practical, but still interesting. So will you go ahead and let's look at the next one. So if we have a solid in water, this is just like that last lab that we did with the copper, okay? When we put that copper in the water. So I want you to kind of figure this out to find the specific heat of lead. It's set up just like the lab we did. So take some time out, pause this, and see how you do. All right, this is what I did. Hopefully it looks a lot like that value that, or like what we did with the copper. So I set this up, we had 100 grams of lead, looking for this value. Here's a temperature change. Here is a negative sign, don't drop that. Here you have the mass of the water. Here you have the specific heat. And here is your final minus initial. Now I put 1.9 here because how many sig figs are in 1.9 after you subtract it? You only got 2 sig figs here. So that's why I rounded my value to 2 sig figs, and then you divide, and my answer again has only 2 sig figs. Why 2 sig figs again? Because when you subtracted, your answer here has 2 sig figs, okay? So check out letter B. Will you do the same thing? This is a lot like the one that we did with the copper in the water. So work through this. When you're done, come back. Okay, welcome back. This was a little bit longer because there's a little bit more math. So I set it up here, all right, and I plugged in my values that I knew. And how do I work through the algebra? I multiply these two numbers to get 4,000. I multiply these two numbers to get 104,000, but don't drop your negative sign. So what did I do after that? I divided both sides by 4,000, okay? So I only had to distribute once on the other side. Why did I decide to divide both sides by 4,000? So I get a positive, or not a positive, a number bigger than 1 on the other side. So whichever number out in front is smaller, divide that by both sides. So now I have final temperature minus 200 is negative 26.1 times this value. Now I distributed, and look what happens when you distribute. What is this kind of number here? What's a negative times a negative? It's a positive. So now I'm going to combine both sides. Now this 1, all right, you probably just wrote that down. But if there is no coefficient in front of the TF, it's a 1, isn't it? So when I add 26.1 to both sides, I get 27.1 on both sides. There we go. And so then I divided both sides by 27.1. I got 36.3. Does that number make sense? I sure hope so. The water value goes up and the metal goes down. So that makes a lot of sense to me. So it didn't go up by much for the water. It went by 6 degrees or so. The other thing came down quite a bit. Okay, so let's go to the next page. Alrighty, Rose. So this is another one, a lot like the ones we've done before. This is a solution. So there's my balanced equation. And why is this important? Because I have 1 mole of barium nitrate, 1 mole of sodium sulfate, and 1 mole of barium sulfate. I don't care about the sodium nitrate. They didn't ask me anything about it. So if you read about it, what's the final thing we're supposed to do? Calculate the enthalpy change per mole of barium sulfate. Well, if you found the enthalpy change per mole of barium nitrate, isn't it the same thing? The coefficients are the same. So go ahead and work through this a lot like the one we did 2 pages ago. So look back at your notes if you have to, pause this, and see how you do. Okay, this is what I did. Solution equals negative Q cal. I figured out the Q cal, and here we go here. Oh, by the way, I had to figure out how many grams I had at 2 liters. Remember, I had to convert liters into milliliters to find the grams there. All right, now what? I need kilojoules per mole, don't I? Well, I got the kilojoules is negative 26. I need moles. Moles of what? Well, it's moles of barium sulfate, but isn't the 1-to-1 coefficient is either barium nitrate or sodium sulfate? So pick one. How many moles of barium nitrate are there? 1 mole. Hey, look what we've done. Isn't it the same number of moles here? Yes, it is. Oh, thank goodness we were smart in our lab procedure here. So it's 1 molar times 1 liter, which is 1 mole. So that's our final answer. Will you go ahead and do problem 39 all by yourself and come back and see how you did? Okay, welcome back. Hopefully you got this. Well, same exact setup. This time had a total volume of 200 mils, so I have a total volume or total mass of 200 grams. I set it up. I got negative 5,600, only 2 sig figs. Why? Because when you subtract, you only get 2 sig figs. So I'm trying to find kilojoules per mole again. I have negative 5.6 kilojoules. And now I need moles. Well, again, the coefficients are identical, so pick one. It makes no difference. We use the same molarity and the same volume. So then I find, whoops, come back here. Oops, don't do that. And now I find the, there it is, negative 56.0 kilojoules per mole. Again, if you have any questions, please write them down and ask me the next time we see each other. I hope this helps you. Don't wait to be great. See you next time. Bye-bye.